Hi students. In this lecture, I am going to discuss problems from IRODOV. Let us see first one. See the question given. The kinetic energy of a particle moving along a circle of radius r depends on the distance covered, S, as t equal to a s square, where a is a constant. Find the force acting on the particle as a function of S. So it is now following a circular path. So force means it is having two components. One is along tangent known as tangential force, and one is towards the center, which is known as centripetal force. Okay, let us see how to start. So see first the data given. It's a kinetic energy given as a function of distance covered. So K equal to, it is a s square, where s is distance traveled. So it follows now circular path. So it follows circular path. So force is having two components. So one is towards the center, known as centripetal force, and one is along a tangent, tangential force. Tangential force equal to mass into tangential acceleration, and centripetal force equal to m into v square by r. Okay, let us see from here how to get these two components. This is equal to half m v square. Okay, so here we want m v square by r. So directly from here m v square. So fc value in the place of m v square 2a s square 2a s square upon r. So it is direct one and very simple one. Calculation of fc. Okay, cross check once. M v square 2a s square upon r. Okay, now focus on how to get tangential acceleration. So we have learned that tangential acceleration is defined as the rate of change of a speed with respect to time. So here v stands for speed. Let us see how to get it. So it is now derivative of speed. So in this half m v square, v stands for speed. So from this we can get a speed. So v equal to 2a by m 2a by m under root into s. Okay, that is v value from the given data. Now substitute that here. Root of 2a by m into s. Now this is a constant. We can take it outside. Now derivative of s. And here s is given. It is a distance traveled. Now it is the rate at which distance is covered. That is known as speed. That means it is now root 2a by m. I am taking that outside. ds by dt, that is equal to speed. So in the place of a speed. Now take this value here. It becomes 2a by m into s. That is now 8. So m into 18, that gives tangential force. So tangential force equal to 2as. Okay. So we got now tangential force and centripetal force. So now we have to find force on the particle, which is nothing but resultant of these two. So between those two components, angle is 90. So it is now square root of sum of the squares. Then see how much we get here. So square of this. I can take in both 2as, 2as outside. I'm taking here 2as outside. Okay, because 2as and 2as remains. So what is left here? 1 is left. So 1 square. Here s is left. S by r. Square of that. It is s by r. Okay. That is our final answer. So simply we have to focus how to get tangential force and centripetal force. Right. Let us see next one. See the question given. A body of mass m was slowly hauled up the hill as shown by a force F, which at each point was directed along a tangent to the trajectory. So your trajectory means path. Okay. Find the work performed by this force if the height of the hill is h, the length of its base l, and the coefficient of friction is mu. Okay. Now see carefully key points in this one. It was taken slowly. Slowly means speed almost zero. Okay. That means we can take delta k equal to 0. Delta k 0 means we can use now work energy theorem. It is taken slowly. So speed is not changing. At the same time, speed almost 0. Next, by a force F, which at each point was directed along a tangent to the trajectory. So this also very important. It is along the tangent. That means normal component, or you can say normal reaction. It is always equal to mg cos theta. Okay. So one more key point is here tangent to the trajectory. Let us see how to start it. Right. First make the given diagram. Here shape is not important. You can take any shape because the answer is not depending on the shape of the path. So you can take here base length. Base length is given as L. It is L. And the height is H. So it is taken slowly. Applying force F always along the tangent means tangential to path. Okay. So your key point is that it is taken slowly. So slowly means speed is almost 0. Okay. Therefore, I'm taking here work energy theorem. Net work is equal to delta K. So delta K equal to 0. Let us say work done by applied force plus by normal reaction by gravitational force by frictional force sum equal to 0. So sum means it is algebraic sum. Means if it is a positive, taking positive value. If it is a negative, taking negative value. Okay. Now in this, by normal reaction, work done is zero. Because if you are taking a small path, means small displacement will be along the tangent. We are taking small displacement. Okay. It is along the tangent. Normal reaction is always normal to that. That means whenever we are taking a small displacement, direction of that small displacement will be along the tangent, and normal reaction is normal to that tangent. That means angle between F bar and ds bar is 90. That's why by normal reaction, no work is done. Okay. Remaining is now by gravity and by frictional force. And here gravitational force is a conservative force and it is a constant force. Therefore, we can write by gravitational force, work done is equal to, it is always vertically downwards. So it is mg. So since it is a constant force, I have discussed earlier that whenever force is a constant, multiply the magnitude of that force with component of displacement along that force. Okay. Here force is along vertical. So I am taking component of displacement along vertical. See, this is now starting point. Let me take it as A. And this is now end point. So displacement means it is a line joining A to B. Okay. That is displacement. It's a component along vertical, that is H, and direction will be upwards. But mg is downwards. So between these two angles, 180. That is mgh. Take here negative sign. Okay. So by gravity minus mgh. Now remaining is by frictional force. So you should be very careful while calculating by friction work done. So I'm taking here one small displacement on the path. Okay. For example, this is now small displacement. Now I'm magnifying that. I am magnifying that. Suppose this is C and this is D. So after magnifying, this is C and this is D. A small displacement ds. Small displacement ds. So this is now ds. Okay. Let us take that tangent. CD is now very small displacement. That line makes an angle theta with a horizon. Okay. So by frictional force work done in that small displacement, see how much it is. Mu mg. It is now kinetic friction. So mu mg cos theta. So here I have taken mu into normal reaction. And remember here, normal reaction will be, it is given that applied force is always along a tangent. So F is along a tangent and weight component, it is mg cos theta. Okay. So since applied force is along a tangent, normal reaction should be equal to mg cos theta. See here one more key point which we have to understand. It is given the body taken slowly. Remember that it is a curved path. It is not a flat surface. It is a curved path. So when it is a curved path, you can take like, this is a curve like this. That means object is following a curved path. If I'm taking a small part, this is a part of a circle. Then free body diagram, this is N and this is mg cos theta. Then I should write here mg cos theta minus n, that provides centripetal force, and that is equal to mass into centripetal acceleration mv square by r, m into v square by r. Since it is given the body taken slowly, so v almost zero, that means it is equal to zero. Therefore n equal to mg cos theta. That's why I have mentioned in the earlier, in the initially, means in the beginning of the problem, the key point is slowly taken. That's why we are able to write n equal to mg cos theta. Okay, right. So it is now mu into normal reaction is mg cos theta. This is now kinetic friction. Mu into displacement is ds. Okay, and between this frictional force and displacement angle is 180, because frictional force down the plane, displacement up the plane. Okay, so I am taking a negative sign. Like this, we have to calculate work done for each and every small displacement. Okay, now integrate. So take sum of all those things. Then see. So I'm taking minus outside, and I'm taking mu mg also outside. Mu mg outside. Remaining is now ds cos theta. From diagram, you can see here ds cos theta means, let us take this easy. ds cos theta means it is equal to the length CE. Okay, I'm taking this length as dl. So from the diagram, ds cos theta is equal to dl. Integration of dl. That means for CD, you can observe carefully. This is now projection length. Okay, this length is now dl. See, if I am taking for each and every small part, for each and every small part like this dl, again dl here, again dl here, like this, we will get this base length. Okay, sum of these dls gives us base length. That means this is equal to minus mu m g l. That is work done by frictional. Now from this, what I can say, by the applied force, work done is equal to negative of work done by frictional force plus work done by gravitational force. And these two are negatives, negative of negative positive. So it is equal to mgh plus mu mgl. That is work done by applied force while taking the block slowly and applying the force along the tangent at each and every point. Okay, so this is our final answer, right? So I hope you got the clarity. Let us go for next problem. A disk of mass m slides with the zero initial velocity down an inclined plane set at an angle alpha to the horizontal. Having traversed the distance l along the horizontal plane, the disk stops. Find the work performed by the friction forces over the whole distance, assuming the friction coefficient mu for both inclined and horizontal planes. Okay, so here we have to calculate work performed by friction force over the whole distance, right? Let us see how to start. So first make diagram for given data. Given an inclined plane, and given here angle is alpha. And see what else given. Block of mass M starts from rest. Starts from rest. Angle given alpha. Having traversed distance L along the horizontal plane. So after reaching bottom of incline, it travels a distance that is equal to L along the horizontal. So this length is given as L and finally comes to rest. And same mass given, angle alpha given, distance L on the horizontal plane given, mu value given. So we have to calculate work done by frictional force, right? Let us see how to start. So here condition is that initially block was at rest and finally block comes to rest. Initially no speed, finally no speed. That means delta K equal to 0. So I can write here work energy theorem. Work done by frictional force. Work done by gravitational force. Work done by normal reaction. Now total sum of this equal to 0 because delta K equal to 0, right? And as usual, by normal reaction, no work is done because when it slides down the incline, normal reaction is normal to incline, but displacement is down the incline. So between these two angles, 90. On reaching ground also, normal reaction is vertically up, but displacement is along horizontal. Again, between these two vectors, angle is 90. That means by normal reaction, no work is done. It is 0. Next, by gravity. It is a constant force and a conservative force. So by gravity, work is not depending on path followed. Okay. Suppose I am taking initially this height of incline is h. That means initially block was at a height h. So mg vertically downwards. So I am focusing simply multiply modulus of that force with the component of displacement along that force. Okay. That means by gravitational force work done, it is equal to mgh. So from that I can say by frictional force work done is equal to, it is equal to minus mgh. Okay. Or same thing we can say like this also in terms of energy. Initially block was having gravitational potential energy mgh. Okay. Finally, no gravitational potential energy and no kinetic energy. So this loss in potential energy is because of the work done by frictional force. So directly also we can say in that way, by frictional force work equal to loss in the gravitational potential energy. So minus mgh. Okay. But in the problem, h is not given. Means we have to get h value in terms of alpha and L and in terms of mu. Okay. Let us see what we can do. So I'm writing once again same equation here. Same equation. Work done by frictional force. So while taking by frictional force, I'm taking on inclined plane. So this displacement will be, if it is h, this will be h by sine alpha, right? Because this is a hypotenuse, h by sine alpha. Then by frictional force work done minus mu. Normal reaction is mg cos alpha. This is now kinetic friction into displacement, that is h by sine alpha. This is work done by frictional force on the inclined plane. So why negative means frictional force is up the incline, but displacement is down the incline. Okay. Next, coming to on the horizontal plane, again by friction work done minus mu mg into L. Okay. This is work done by frictional force. Next, by gravity. By gravity, it is a positive mgh. This is equal to g. Now we have to solve for h because if we get h value in terms of given quantities, that we can substitute in this one. Okay. So h is here and h is here. And in throughout mg that I can cancel mg. So mg, mg and mg. Remaining is now here h is here and here. So h into 1 here minus mu cos by sin cot. It is mu cot alpha. That is equal to taking this one to right side mu n. Okay. Substitute this value in this one by frictional force. Work done is equal to minus mu mgl upon 1 minus mu cot alpha. Cross check once. From here h equal to it is a mu l upon 1 minus mu cot alpha. Substitute this value in this. Okay. Already having there minus and mg. That's why minus mu mg l upon 1 minus mu cot alpha. Now in this we have to substitute the values of mu, m, l and alpha. Then we get the answer. So key point is that starts from rest and finally comes to rest. That's why we have taken work energy theorem. Next we are focusing on how to calculate H because this is equal to mgh minus mgh. Okay.